Hi, everyone. Welcome. Thank you for joining us online today. My name is Samantha Lau. I'm the Manager of Communications and Operations at the Canadian Water Resources Association. Joining myself today is Meg Olson, our Executive Director, and Emmanuel Sims from Environment and Climate Change Canada. As you all know, we have a great speaker lineup. Tadros Gobriel from the University of Laval and Nicolas Gasset from Environment and Climate Change Canada. And they're both joining us for today as part of our series we are hosting with the National Hydrological Service on the research conducted through the Flood Hazard Identification and Mapping Program. Next slide. Sorry, Liz, we'll go straight to slide 3. Just a couple of housekeeping notes before I move further. We have presentations in both English and French. Please be sure to select the preferred language you would like to tune into for today's webinar using the interpretation button where you can find it, the little globe on the bottom of your screen. To view the slides in your preferred language, please make sure to toggle between the shared screens at the top left of your Zoom window. All slides are available in both English and French. Through our Zoom interface, you also have the option to turn on captioning for the webinar if that would be useful to you. Closed captions are available on the bottom panel with the CC icon. Next slide. The Canadian Water Resources Association is a national organization dedicated to advancing the sustainable management of water resources across Canada. Our members include professionals, researchers, biologists, conservationists, policymakers, and many more, all working together to address critical water issues. CWRA hosts a variety of events, including webinars like this one today, workshops, and our annual national conference, which will be held in beautiful Penticton, BC this year. If you're enjoying this webinar series, please be sure to check out the other great events that we have available on our website. We will post a link in the chat to our events page. You will also have the opportunity at the end of today's webinar to provide feedback to our team. Next slide. This webinar is part of our 2025 webinar series in collaboration with ECCC's National Hydrological Service. As part of this exciting series, we are highlighting groundbreaking hydrology and hydraulics research conducted through the Flood Hazard Identification and Mapping Program. You'll hear a little bit more about this later, and showcasing the latest advances in flood mapping science across Canada. This series is designed for flood mapping practitioners, researchers, interested parties, and the general public, offering a unique opportunity to hear from subject matter experts at no cost. These webinar recordings and some of the accompanying materials will be available on our website after the sessions. So I'm seeing lots of new and familiar names joining us today. If you would like, and I highly encourage it, please say hi in the chat and share where you are calling in from today. As a national organization, we acknowledge that the speakers and our audience are all joining us here from different locations. I would like to acknowledge the land on which I work and play on is the traditional territory of the Haudenosaunee and Anishinaabe people. The territory was the subject of the Dish with One Spoon Wampum Belt Covenant, which is an agreement between the Iroquois Confederacy, the Ojibwe, and allied nations to peacefully share and care for the resources around the Great Lakes. CWRA has created an Indigenous Relations Committee to support the organization in its work towards reconciliation and allyship with Indigenous peoples and sustainable and effective water management in Canada. This is important to us, and we are committing funding, volunteer, and staff time to this work. We welcome any and all feedback and advice on this journey. Okay, before we dive into today's presentation, I'm pleased to welcome Emmanuel Sims from Environment and Climate Change Canada. Emmanuel will be providing a brief introduction to the Flood Hazard Identification and Mapping Program. Over to you, Emmanuel.
So my name is Emmanuel Sims. I'm a water resources engineer with the National Hydrological Service in Ottawa, Gatineau. In the next slide, Liz. Here's a quick overview of the Flood Hazard Identification and Mapping Program, known as FIMP. The FIMP launched in 2021-2022, and the continuation of the program launched in 2023-2024, with the current program ending in 2027-2028. Natural Resources Canada leads FIMP in close collaboration with Environment Canada and Public Safety. FIMP funds flood mapping projects in close collaboration with provincial and territorial partners. Cost-sharing program is 50-50 with provinces and 75-25 share in territories. In the breakdown of the program funding above, the flood mapping projects with provinces and territories are included in NRCan's funding. A goal of FIMP was to contribute funds to research. Environment Canada funds research streams dedicated to incorporating climate change into flood maps. This webinar series focuses on the outcomes of research funded by Environment Canada completed during the first phase of FIMP. NRCan funds research streams related to regional flood modeling and inclusion of Indigenous traditional knowledge into flood mapping projects. We look forward to sharing the outcomes of the research with the larger community. Next slide, please. The next webinar in the series will take place on March 12th, featuring presentations from James Craig, Jonathan Jalbert, and Brian Tolson on innovations in enhancing hydrologic data and extreme precipitation analysis. For more details on upcoming events, please visit the CWRA website. And with that, I'll pass it back to our host, Sam.
Thanks, Manuel. Next slide, please. Okay, so it looks like a few more people have joined us, so welcome again to our webinar. I just have a couple more notes and refreshers on housekeeping, and then we'll get started with the presentation. With regards to language and interpretation, please be sure you're listening to the presentation in your preferred language. You can adjust this on the interpretation settings on the bottom of your screen. To view the slides in your preferred language, we'll have different people sharing slides today. Just make sure you're toggling the slide option at the top left of your Zoom window. All slides are available in both English and French. Closed captions are also available, and you can find that on the CC icon at the bottom of your screen as well. We are recording this webinar, and the recording will be freely available on our website over the next couple of weeks. During the talks, we might post some links as well in case you want to save those to follow up on, so please check your dashboard for those in the chat window. We will take a few burning questions in between each presentation, and then again after the panel discussion. If you have any questions or comments at any time, please type them into the Q&A tab on your control panel. If you run into any issues on the Zoom platform, please message us in the chat and we will try to help you resolve them. And if you find yourself disconnected from the webinar at any point, please just rejoin using the same link once you've restored connection. Next slide. Now for a quick introduction of our first speaker, Dr. Gabriel is an assistant professor at the University of Laval and an expert in river ice engineering. His research work focuses on understanding the different river ice processes from early phrasal and anchor ice formation, the breakup ice jams, and ice jam flooding. Dr. Gabriel is collaborating with several governmental agencies and researchers to develop mitigation methods and early warning systems for ice jam floods. He's co-authored more than 50 publications in peer-reviewed journals and conference proceedings and has supervised over 20 graduate students. Thank you so much for joining us today, Dr. Gabriel. I will pass it over to you for our first presentation.
Thanks, Sam, for the introduction. If I may, I will just start sharing my screen here. And then let me know if you can see my presentation.
That's great.
Yeah, good. Okay. Thanks, Sam, for the intro. Welcome everyone to this webinar and this presentation. I'm very honored to be presenting here today. Again, what I'm presenting is not solely my work. I'm building on the shoulders of many great grad students, collaborators, professors from other universities, CRIBE committee, if you're aware of the CRIBE committee, colleagues at Université Laval, and then colleagues at ECCC, colleagues at NRC, or lots of other collaborations that I will be mentioning during the presentation. So the title, I've made it a little bit wider title. So it's basically multi-methodology approach for predicting ice-related floods parameters. So I intentionally decided not to say ice jam floods in the title because sometimes we're not very sure of the definition, or sometimes ice can cause some problems that are not defined as ice jams, and this is actually included as well in the methodology we're developing. A quick intro why river ice is important, because it's basically covers maybe from 2 to 3 months a year up to 6 to 8 months a year. Our rivers are covered with ice. So imagine if we are obscurely monitoring those rivers during the ice affected period, and then our forecasting methods or our forecasting power is actually affected during a huge period of time. Breakup is basically the transition from an ice cover period to an open water period, and this is a very interesting period where there is an effect of meteorology, precipitation, heat, fluxes, and then the hydraulics of the river itself, and then also the morphology of the river, how the flow and the slope and the configuration of the river itself is affected or is affecting the rest of the processes. This makes the ice jam flood, which is abbreviated here as IGF, forecasting procedure being very, very challenging and complex, and this is why it's an area of research that is still developing strongly up to now. A quick overview of what are the types of breakups that we're facing. So we call it a thermal breakup if it's very similar to a lake melting. So what I mean by this, there is an ice cover, and this ice cover is now in the river with very low flow, and you have some heat added to the ice cover, either by slow precipitation, solar radiation, or warmer temperature, and then it melts in place with no issues. And then this is the best case scenario. There is no flooding risks or any damages to forecast. But the other procedure would be a dynamic breakup. So this is basically when we have lots of precipitation or an increase in the discharge due to rapid snow melt or whatever, and then the ice cover has not had the chance to actually weaken or deteriorate in place, which makes it lift up and then start to actually break with transitional and longitudinal cracks. And then as the flow increases, those pieces of ice blocks start to make their way downstream. Some of them can actually pass through the constrictions, but the ice is easily congested when there is a place to do so. All of this to say that the interaction between the three components, which are the meteorological effects, the morphological effects, and the hydraulics in the rivers, are actually very complex, and to integrate all of these together so that you're able to predict what's happening in the river during breakup is a challenging task. Saying this, it's not like nothing has been happened so far. Like lots of work has been progressing in the past maybe 50, 60 years, but remains some big questions. So an ice jam, when it forms, what would be a discharge or a threshold discharge that would cause a dynamic breakup and consequently an ice jam? So this is a tough question because already the under ice discharge is a big challenge. Another question is, when will it actually start to break? What is the onset of breakup? So there is an ice cover, and then once we start seeing those cracks and lifting, this is a critical point where we start predicting a formation of an ice jam. So when will it start to break? That's another big question. And then once it breaks, where are the spots where a jam would form? And then finally, if we have a jam, would it actually cause flooding, or it's just a local accumulation of ice and that's it? This is another big question as well. So we're talking about severity, We're talking about location, extent, timing. Those are terminologies that are important to retain. An overview of what have been done in general to address those questions. So there are hydraulic models that can simulate ice jam, either a steady model where you can just tell the model there's a jam here, and then it can predict the hydraulics to tell you what is the maximum water level, like HEC-RAS and so on. There are some process-based models like CRISP and River 1D, but those are basically hydraulic models that are needing the input to actually predict the jam. Another step ahead is actually to integrate a hydraulic model with a hydrologic model. So HEC-AGM-S with HEC-RAS, this has been tried, mesh with Riv Ice, and then us here in Laval, we're working on Hoopla with HEC-RAS, which has I will present some result of this later on today. And then also we have data-driven methods. So those are either threshold models, regression models, or models that are basically based on some historical analysis of data, or we have empirical methods, which are basically conceptual methods that tells a story in a conceptual way, or purely artificial intelligence methods or purely machine learning methods that are independent of the physics that is happening. And finally, we have also real-time monitoring, which is either remote sensing or a network of an early warning system with water level sensors or cameras or whatever. Those are also used to predict ice jams with some level of confidence. Us here in Laval, we're working on coupled Hoopla and HEC-RAS models. So to answer the question of what discharge is actually causing the jams, we're also working on data-driven methods. I will go over them today to answer the rest of the question. So when will breakup start? What is the onset of breakup? Will it actually jam or not? Where will it jam? And if it jams, what is the severity of this jam? What is the actual expected maximum water level at this location? So to put you in context, we've developed here at Laval in collaboration mainly with the Ministry of Public Safety of Quebec, MSP, and also with ECCC, and then the Ministry of Environment, MELCCFP of Quebec. We've developed a very comprehensive research program at Laval for river ice research. This has started with Professor Brian Morris in 2018-19, and then when I joined Laval, I extended the research project to have an integrated vision to actually answer most of the questions related to river ice problems. So to navigate you through this flow chart, I would start with the blue rectangle that it's stating under ice discharge. So if we can answer this question related to predicting under ice discharge, it will be a key component for the rest. So it will basically feed the effect of tributaries. So if we know the under ice discharge, we can know if a tributary would actually cause a jam or melt a jam. So the timing and the level of discharge or the threshold discharge that will cause a jam at a confluence. So that's another project. Also, it will be used to develop the methods and criteria to anticipate flooding by ice. So this is really the orange rectangle here that is the core of today's presentation. And it will be fed as well with methods and criteria will be fed as well with a knowledge of blockage by frazzle ice and anchor ice. That's a side hazard of river ice as well that is integrated in our research ideas and research plan. And once we have these, we can do two main things. We can either develop early warning systems that can predict the formation of ice jam and ice jam flooding, or we can confidently assess or develop mitigation measures. And we have two other projects on this, either structural measures like ice control structures and booms and stuff, or non-structural measures like ice weakening using amphibex or ice cutting or whatever other method to weaken the ice before the breakup. So this is an overview of the research program developed at Laval in collaboration with the rest of of the agencies. In today's presentation, I will focus mainly on this orange rectangle here, methods and criteria to anticipate flooding by ice, and which has to touch with the under ice discharge, which is the main input to our methods and criteria. Before I go into the methods in details, I want to talk a little bit about the study site. Where in our team we call it's our outside lab. So we have a lab that is called the Chaudière River here, just south of Quebec City, where it's very famous for flooding. So it has a catchment of 6,700 kilometers squared. It's a 190 kilometer long river. It's split into basically three parts. The upper Chaudière has a steep reach. The intermediate Chaudière is very mild, and then the lower Chaudière is steep again, and then it discharges into the St. Lawrence River. Our focus is the intermediate Chaudière. If you see on the left map here, is basically from kilometer 103 up to kilometer 39. So we're talking about 60 something kilometers, 65, 69 kilometers here in the intermediate Chaudière. And the slope in this area is around 0.5 meter per kilometer, so 0.05%. So it's a very, very mild slope, and it's very famous for ice jam flooding. Yearly ice jams are forming in this river, so we can predict it very, very clearly. The locations and our monitoring stations can be very accurate in this site. We have lots of towns along this river: Scott, Sainte Marie, Saint Joseph, Beauceville, and Saint George. Those are some of the main towns in this intermediate Chaudière. An area called Dead Waters or Eau Morte en français. This is a really flat area where most of the jams occurs. What we've decided to do is basically get this under control. So we said enough with scarcity of data. We're here to understand every single process happening along this 60-kilometer stretch. And up until now, we have 4 years of comprehensive field monitoring of this river. And from 2018 up until last year, and then this year we're continuing the monitoring as well. Our program is extended up until 2027, so we have funding to continue our monitoring. In terms of instrumentation, we have 2 weather stations. One is Environment Canada at Beauceville, basically at kilometer 83 here, and then at Saint George and at Scott we have 2 provincial Minister of Environment of Quebec stations to complement. Those are weather stations here. We have hydrometric stations to two hydrometric stations at the input, one at the main branch of Famine, one at Sartigan Dam here, and then we have one downstream for discharge. Those are giving discharge, and then along the way we have 6 stations along the towns in the intermediate Chaudière giving continuous water levels, as well as at Thieu-Laval we added quite a few temperature and pressure sensors as well. During those winters, so we go out basically on a weekly basis every Tuesday to do under ice measurements and ice thickness measurements in key locations. Those are added as well. We added trail cameras along key locations, taking pictures of the processes, as well as drone flights whenever there is a movement of ice. We complement the rest with satellite images, Sentinel and Landsat. We have a complete bathymetric survey of the river, which was used to develop hydraulic models. Now we have a HEC-RAS model calibrated for open water and ice condition as well. So all of this to say that we try to have a full control of what's happening almost in each kilometer of the river. And then after this, Gabriel, one of the students, went on and invested in the archives of all the towns and all the journals and all the data, even before the monitoring system was implemented. So the monitoring system was implemented in 2015, but he went back from 1968, basically from the construction of the Sartigan Dam upstream of the intermediate Chaudière up until 2015. and on each town, he recorded the date of maximum water level, and from journals or other sources or images or interviewing the locals, he was able to estimate a maximum water level related to ice breakup events. And then he categorized those into 4 thresholds for flooding, depending on the color here. And then the towns have actually levels of intensity. So this is an incredible historical data that has been we have invested a lot to develop this, and then this will be used later as research progresses. So now we're ready to answer the question. Now that you know the sites a little bit, you know the amount of information we have, and then like if you remember the flow chart of the integrated research program, one of the main outputs was inputs to the methods and criteria to anticipate flooding by ice is actually what is under ice discharge, or a ice or a discharge during a jam, or any ice affected discharge. We decided to adopt the coupling model coupling idea. Basically, we said, okay, if it's an operational system, so we need to have a model that is easy to run with less amount of information to be input. So we decided to go with a HECRAS model for the ice cover, which is an unsteady model, or when we can switch to an ice jam steady with a daily time step, so it can be run once daily if we need to simulate ice jams as well. And we decided to use the Delfuse platform developed by Deltaris in the Netherlands. And the platform is very flexible. So we integrated the Hoopla, which is a hydrological ensemble model that basically it's a rainfall runoff model, very, very basic model in terms of processes. It takes just precipitation and temperature, and it has a snow accounting routine, but it has 20 embedded models that are run on a 3-hour time step, and then it produces ensemble hydrographs with uncertainty calculations, those to be input into the HECRAS model. And then the HECRAS is basically fed with an ice cover thickness, extent, and roughness. And then we have water levels along the river. And then we can match those with measured water level, and then check the error, and then calibrate the models to have a better prediction of a probabilistic prediction of water levels and of discharges along entering the flow, entering the domain. And then with those discharges, we have a better understanding of the range of accurate discharge. This is a quick snapshot of how the Delfuse was developed. It's a very, very flexible and difficult to develop platform. We've integrated radar data. We integrated CASPAR as well. All the forecasting from Environment Canada has been integrated in the Fuse as well. We have satellite images being fed in the Fuse system. We have 2 HECRAS model. One, when I say steady, so I mean we can run it on a time step that is of the Fuse system, and we have the unsteady for stable ice cover that is run continuously in terms of the platform. And we included all the modifiers that are used in the HECRAS model as parameters. So the operator can actually only open the Fuse system and then modify the parameters for HECRAS and run it through the system in one place. Some of the results we had from this exercise to be published soon is that if you can see, the top 3 time series are discharged with time at 3 discharge locations, and then the bottom 2 are water level or stages at 2 locations along the river, Sainte-Marie and Saint-Lambert. For the first day, so there are 3 days of forecast. Those are black vertical lines. So the first day when the Hoopla predicts a hydrograph with the first measurement of discharge day at about, let's say, at the upper Chaudière at 100 meter cube per second, And then this is translated in the bottom graph with a very good agreement with water level. And as we progress in the forecast, this accuracy actually decreases. And this tells you that there is lots of confidence in the water level measurements to give us a good idea of the discharge, rather than believing the discharge that is coming from a hydrologic model to try to have an estimate of discharge. So this coupling modeling criteria or methodology is very interesting. We're exploring a little bit more as we go. There is a paper coming out in hopefully soon that will discuss those details. So that's the very first approach to have an under ice discharge. The second one would be the empirical methods. So remember, there are two components that we're dealing with. One is the coupled modeling, and the other one is data-driven. So for data-driven, there are three ideas that we're exploring as well. So one of them is an empirical model, and the idea behind it was developed by Professor Brian Morris and Dr. Benoit Turcotte in 2017 or 2018. And then the idea is very simple, is basically we have two kind of forces acting against each other during breakup. One is the driving force, which is basically the hydraulics or the discharge, and the resistance force, which is mainly the ice cover thickness. So we're not integrating all the other morphological effects or whatever, just very simple empirical model. And then as the flow discharge is high, and we have a thin ice cover, and then it can actually go and at a breaking point, which is basically the earliest breakup possible, when a thin ice cover is matched with a very high flow, and then it breaks the ice cover. There is no big problems at this stage. But as we progress further, if we have again a high discharge and a very thick ice cover, we'll have a mechanical breakup that is very disastrous, and that's the worst case scenario. But if we have on the other side a low discharge and a thin ice cover, we have a thermal breakup. And then as this thermal breakup progresses, there is a point in time where we have the latest breakup possible, where we have a very low discharge and a very thick ice cover. There is no dynamic breakup. It goes and tends toward a weak dynamic or a thermal breakup. So based on this criteria, they developed a graph that is presenting basically the discharge on one axis and the resistance, which is they chose the parameter of cumulative degree day of freezing or thawing as a representative of the ice thickness. So they said the amount of cold days is directly related to the ice thickness in the river, which is a true assumption. And they put historical flooding events along those axes. So on vertical there is a discharge, on the horizontal there is a cumulative degree day of freezing or thawing, and the dots are basically peak events with ice jam floods, so white dots. And then they define the zone based an empirical zone based on those points. So the physics behind it is a little bit empirical. That's why I named it an empirical model. And then what we did to try to improve this is to say, okay, if we're not accounting for all the other inputs to the ice cover in terms of heat, we might as well replace the cumulative degree of freezing or thawing with net heat to the ice cover. So we did this same exercise for on one of the sites. So the previous slide was actually combining on a big reach, and then we decided to actually go on one site at a time. So for freezing degree days or accumulated net heat during the freeze up, the trend is hard to follow, but there might be a trend. But during breakup, we might be able to draw a red line here that says there is a relation between the discharge and the cumulative cumulative heat to the ice cover. Well, we're progressing and trying to explore this idea a little bit more to be in operation. So the Ministry of Public Safety of Quebec would have would have a line like this, and then we'll monitor discharge and cumulative heat in real time. And then we'll say when it goes above this red line, and then we can send an alert. This is the idea, to have a simplistic model of this. The second idea is to have a threshold model or regression model, and building on our extensive knowledge of what's happening in processes along the river, we said, okay, there's an opportunity here to go and define those parameters using thresholds. So here, this is a graph showing the stage of the river. So those are the kilometers in the intermediate chaudière, and then on vertical here we have the date of freezing over the date of breakup, reference to the 1st of October. So 1st of October is day 1, and then freeze up if it's, let's say, December 30th, and then it will be 60. Then if breakup is March 1st, it's going to be, I don't know, 120 or whatever. And then the ratio of both in terms of purely the time. And then this red line, or the blue or the black, those are the 4 years that we've monitored. So sorry for the legend here is not showing the 4 years, but the first 2 years, which are black and blue, were dynamic years, and then the other two, red and green, were actually thermal years, and the ratio is somewhere here. This is not very helping at this stage, but the onset of breakup or the date of breakup would change a little bit along the river based on this ratio. And then there is a band, like we can actually follow a band around 0.5, 0.4 between the date of freezing, the date of breakup. It has some physics behind it, because the longer the winter, the thicker the ice. But anyways, this is purely the dates. We did the same exercise to have a unified threshold for the ratio of freezing discharge over breakup discharge. So basically, once the ice cover forms, what was the discharge of the river, and then when it started to break, the onset of breakup, what was the breakup discharge. And then when I see a ratio of 0.1, it means that the breakup discharge was 10 times the freeze up discharge, something like this. So for the two dynamic breakup, so we can see the range is fairly consistent, except of those peaks. Probably those are confluences with smaller tributaries. And then there is a line that can be drawn along this, and then we can say, okay, this is really consistent. The ratio is starting at 0.1, and then it goes down to 0.5 along the river as you go downstream. And then when we add the two other thermal years, and then we realized that the thermal year didn't work well at the upper reach of the intermediate chaudière, but it did work well on the downstream reach, or the other half. So this was interesting, and then it opened our mind to another idea, is, okay, why don't we look, as well as if we're looking at the discharge, let's look at the cumulative degree day of thawing over freezing. So that's basically what it says physically, is how much weakening of the ice have been occurring before breakup happens. So if the cumulative degree of freezing is a representative of the thickness, and then the deterioration of the thickness is a cumulative degree day of thawing. So the ratio of both, how I read it here, like if we're reading a ratio of 0.5, it means we need to add a heat that is half of the heat that have been used to develop the ice, to weaken it before breakup starts. So that's how I read it. And then when we added the 4 years, again, sorry for the legend, and then we can see clearly that there is a range here that can be followed for those two for this ratio here. So clearly there is a split here in the river, where the discharge is the control at the downstream section, but at the upstream, probably the heat is the control. And this led us to go a little bit further and to develop a reach by reach threshold criteria. So for this, because we know I can't say every, but we know the river in details as much as possible. So we split the river into 500-meter section. For each section, basically, that's a PRG project of AHAB, co-supervised by Amy Shi from University of Alberta to actually look at the morphological indices for each one, so we can understand a little bit more what is the effect of the morphology. Since there is a split here, we need to understand a little bit more. And then we looked at those different indices. I'm not going to go in details, but basically a width index, a sinuosity index, a slope break index, and bank slope, society slope index. So for these ones, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have a combination of morphological parameters that have been calculated for each 500-meter segment of the river. And then we developed a combination of those parameters, and we try to actually non-dimensionalize them, or basically equalize the effect of those parameters to see which reach is governed by which parameters. And we did a PCA analysis for this, and then with the PCA analysis, we were able to use data clustering to actually group them into different clusters. And then based on this, we were able to actually define a group of morphological parameters that are controlling each reach of the river. And you can see here the different color codes, so red, green, blue, yellow, whatever. Those are reaches that are controlled by a group or a combination of morphological parameters that are the most important ones. Which one to choose for each one? And then it was a simple criteria. We compared it with measured data, and then the one that has basically the highest R square and the lowest root mean square would be chosen for each cluster. And for example, here, this is just one example to predict the date of breakup. It was the narrowing index, the relative slope break, and so on. Based on this, I will show just one example of the results as well. We have the input parameters, which are all of the parameters, the freezing discharge, breakup discharge, and then narrowing, and so on. And for each cluster, we would choose the morphological parameters that are most affecting this cluster or this reach of the river, and it will give us an equation that can predict the date of breakup. So results here on the vertical is the date of breakup, on horizontal is the stationing, and then in red are the observed date of breakup, in yellow are the modeled, using each cluster. So each point here is referring to a different cluster of the river depending on the kilometer, and you can tell very quickly that there are some sections that are a strong factor of the discharge and the CDDT and CDDF or ADDF. And there are other sections that are basically cluster 5, for example, is just a function of the discharge. There is no effect of morphology or effect of the heat. So this is an interesting venue that we're exploring a little bit more. IHAB is working on the rest of the years to actually develop the same model for the rest. Finally, for data-driven, we looked at artificial intelligence methods and data-driven methods. This is still in progress. Amir is co-supervised by Professor Hossein Bonagdari from University of Ottawa to work on this. We just published those results in Cold Region Science and Technology for a review of AI methods for predict ice flood. Honestly, this was an area that is very new to me. And then I talked to Amir. I said, listen, each time I read a paper, it comes up with a new abbreviation, LSMT or LGTV, I don't know, or whatever the abbreviation is for a new method for machine learning, and then makes me a little bit puzzled, like where are we and what is the big picture? And this was the very first GNC funding from ECCC that we worked on, basically laying out the foundation of what is the framework for artificial intelligence for IceJam flood. So for this, we reviewed the IceJam databases, and then we figured out in this plot here that over the years from 1997 up until last year, there are 4 categories that are used to predict. So we're used AI to predict IceJam. So there is the occurrence, which is binary, 0 yes or no IceJam flood. And a step a little bit further is the severity that comes with maximum water level if there is an IGM flood, and then the timing, and then the location. And then those on vertical is a number of studies that as we progress, more research is focused on this way. And then for each of those publications, we reviewed the input variables, which are either raw or dependent variables, and the frequency of usage. You can refer to the paper of Amir, and then you can find more details on this. And then we reviewed the methods themselves. For the databases, we're very proud in Quebec here. The Ministry of Public Safety is maintaining a database of all the IGM floods as much as possible through their local or regional offices. Whenever there is an IGM flood, a person would go record the maximum water level, the location, and so on. It's an interactive map, as well as we talked about the historical flood events, HFE, by Natural Resources Canada, or the CRID as well. There is an effort to develop a national database for IGM flood, which is very important to develop our models. This is just an overview of the general input parameters, but for each category we have more details on this in the paper. But it tells you very quickly that an air temperature, precipitation, discharge are very very extensively used for the different categories, which are occurrence, severity, timing, and location on the vertical. And then when we looked at the AI methods themselves, so basically, if we have machine learning, this is the mostly used, and then ensemble is basically repeating the machine a few times with different clustering of data. And then hybrid, when you combine machines together, and then framework when you basically input or integrate a machine learning process with another process-based model. And then, as you see as well from our review, machine learning are used for all the 4 categories of IGM flood prediction. And then the ensemble wasn't used for location, but was used for the rest of the categories. Hybrid as well was used for occurrence and timing only, not severity. And framework was used for severity, which just makes sense when you include physics with machine learning. So you need model to have the severity, and it is used for the location as well. Briefly, because I'm not gonna take this, because this is the PhD project of Amir, and then he has a very interesting way to integrate things. I'm probably gonna present in future webinars. But just to lay the ground, if you are not familiar with machine learning, don't be intimidated, because I was at the same boat. I learned as we go. And I learned that machine learning processes are basically the simpler process. It's one layer of input. It has many black box interrelationship criteria to have the output that you need, and either use artificial neural network or k-nearest neighborhoods. It depends which is the nearest, adaptive neural fuzzy, or whatever the ANFIS. The good thing about this is that it's simple. It's just one set of input, and you calibrate the output. It's only the number of layers that you calibrate, or the hyperparameters. It's of course less accurate and very sensitive to data liability. We use the simple machine learning one step in complexity, which is the ensemble, and then the ensemble is using multiple machines. Sorry, multiple times the same machine by combining machine learning with data clustering, or bagging, or bootstrap, or stacking, whatever is the method to actually divide the data and then go over the same machine, and then you can improve a little bit the prediction. It provides better accuracy, and with data bragging or bootstrapping, you can have less dependency on data quality. It's of course much more sophisticated, and it's harder to calibrate as you move further. And based on our review, it's used for occurrence and timing, which makes sense. Another level of complication is the hybrid, basically using multiple machines instead of the same machine with data clustering or whatever. You use multiple machines, but the input from one machine to another, you have to have a meta-heuristic algorithm to tell you how the data will be sorted and how it will be input to the second machine and so on. And this is where you can see CNN-LSTM. Those are the kind of abbreviations that used to intimidate me before I started this. So the good thing about it, it's more accurate because you're combining machines together. It's simpler than Ensemble. There's no data bragging or bootstrapping, less reliable on data quality, but it's of course harder to calibrate because you have this step of meta-heuristic algorithm that you need to define, like how the data will be, the results of one machine will be introduced to another machine. And then finally, the framework approach, which is sometimes they call it integrating physics-based process with machine learning, and this is an interesting venue, especially for severity, because you need to actually, once you have the knowledge, you need to put it into a hydraulic model to see what is the maximum water level. So an ice jam, yes or no, discharge, what is the discharge, and so on. The machine can help. And then to predict the accuracy of a maximum water level, maybe this is where you put into a hydraulic model and get you the severity of the event. Of course, it comes with a complication that you need to calibrate another process-based model. So for this example here by Leo et al. 2022, Rev ICE model is a process-based model where you have to calibrate all the ICE processes parameters. By this, I will conclude an overview of our research program at Laval. I'm not touching on the mitigation measures or the frazzle or anchor ice blockage of intakes and flooding, not touching by the effect of tributaries and rain on snow that I didn't even talk about. That's a colleague that is Daniel Nadeau at Université Laval is working on this on the same funding framework. So with this, we're planning to go further for future work to integrate satellite imagery, graded data, and so on into our Fuse system, and this will be input to our operational model. This thresholding technique is very promising. Up till now, the results that we're having is very, very interesting. We'll do some sensitivity analysis and validate a little bit more, and then if it works, and then that would be super interesting for the operators. So it's just a ratio of parameters. The empirical method, which is the method that is initiated by Professor Brian Morris and Benoit, will take it a little bit further and make it operational with collaboration with Benoit Turcotte as well. And hopefully with the AI-based method, the PhD of Amir will be able to integrate physics-based with a cascade of models. So our idea is to actually have a hybrid and an ensemble, a framework and a hybrid model at the same time. So that's our approach for this. I want to acknowledge the Ministry of Public Safety of Quebec, which is our main sponsor and a collaborator, as well as Ministry of Environment of Quebec and as well as Environment and Climate Change Canada for this opportunity. Thank you for your time.
Thank you, Dr. Gabriel, for sharing your insights today. Just a reminder, if you have any questions, please type them in the questions tab. I think we have time for maybe one or two of the questions that are already submitted. So from an anonymous attendee, does the flatness of the Chaudière River in the 60-kilometer reach studied mean that it has more jams than the steeper reaches up and downstream?
Yes, it's even called in French zone des eaux mortes. It translates as the zone of dead waters. So it's a very, very flat, so 0.5 meter per kilometer, 0.05%. It's a very flat reach compared to the upstream and downstream, with lots of meandering and islands. So it's very prone to ice jam flooding. So that's true. Like the slope itself is a big factor, and it has been incorporated in our predictive model. So yeah, that's correct.
Thank you. And then a second one, I believe this was regarding the threshold model. The relationship between river stage and flow rate is relatively uncertain with the presence of an ice cover as compared to the open water relationship. How were the freeze up and breakup discharges determined?
There are metric station by the Ministry of Environment of Quebec that are operating on the river. So we use the upstream discharge that is reported, that is a corrected winter discharge, as our input. So hopefully with our project for the coupling model would give an insight of the level of uncertainty for those published discharge, because we do our weekly measurement during winter for the past now 5 going to 6 year. So with our manual measurements and with the current funding with ECCC, we'll be able to correct those discharges a little bit more. But for the current results, we use the published discharge by the Ministry of Environment of Quebec.
Thank you so much. I still see some questions coming in. We will save them for the end of the webinar, so please keep them coming in. Make sure to type them into the Q&A so we can keep track of all of them. So thank you, Dr. Gabriel, again, and I will move to introduce our second speaker. Nicolas Gasset is a meteorology and numerical forecasting expert at Environment and Climate Change Canada. After earning a mechanical engineering degree from INSA Rouen and a master's in environmental studies at the University of Moncton, where he developed the first public wind atlases for New Brunswick and PEI. He then completed a PhD on large-scale atmospheric simulation. At ECCC, he developed the Canadian Surface Reanalysis forecasts and contributed to key operational forecasting systems. His expertise in numerical modeling, reanalysis, and technology transfer has led him to a research scientist role overseeing RCAS. We are super grateful for Dr. Gasset for his time presenting with us today. So then I'll pass it over to Nicolas.
Bonjour, je vais prendre le contrôle de l'écran. Okay. Voilà. Est-ce que vous voyez bien mon écran?
Can you see my screen?
Oui.
Oui, ok, parfait. Donc bonjour, donc aujourd'hui je suis heureux de
Okay,
vous
so today I'm glad to present
en fait, la réanalyse canadienne
well,
de surface,
the Canadian Surface
qu'on appelle,
Reanalysis, the
en
CASR,
anglais,
CASR in French,
c'est important de noter
CSR or CASR.
il me demande le langage que je parle, 2 secondes, en français.
Sorry, I just need to tweak my Zoom settings here.
Voilà. Donc, ça s'appelait avant, la réanalyse canadienne de surface, on appelait ça
So the
RDRS.
Canadian Surface Reanalysis, but it changed its name. It's now called CASR or CASR. So it's the work of several people at the Canadian Meteorological Center, and it's a big collaboration, which had lasted for several years. So I'll present the method, its characteristics, and the results of the last version of CASR. So why reanalysis? And why do we do these reanalysis? Well, a reanalysis, it's combining meteorological observations of the past with simulations of models and digital forecasts to provide a history of the weather. So this is a definition which is quite practical. It's useful for observational studies done over several decades normally, so it allows us to have the possibility of analyzing the high impact events, for example, floods or extreme events. This also allows us to do atmospheric studies. Well, it's used as a reference, historical reference for climate runs, and we can see the evolution of temperatures over the decades, for example. Initially, the reanalysis were atmospheric.
Nicolas, sorry, I'm going to interrupt you.
Sorry, Nicolas.
Your screen, we can't see it anymore.
You can't see my screen anymore. Okay.
No.
Okay, so now?
Yes, we can see it now.
Is it the proper one? Yeah, okay. So I don't know. Okay. Donc je reprends. Vous m'entendiez par contre. Donc en fait c'est ça. Initialement les réanalyses elles étaient atmosphériques.
So initially reanalyses were atmospheric. Now they extend two different Earth components.
s'étendait sur plusieurs décennies, mais maintenant, on
We've
a
done
de
for
plus en
several
plus de
decades, but now we have more and more reanalysis that are for
composantes
various components,
environnementales. Donc,
environmental component. So reanalysis for ocean, for surface, for carbon cycles. But basically, these reanalysis were global and covered several decades, but now they can be regional and even cover a whole century or a few decades. One unintended effect is a huge amount of data generated by reanalysis. And these reference databases allow a training, artificial intelligence, machine learning. So these reanalyses are also used to train these AI models.
OK. Donc, pourquoi, en fait, quelle motivation
So why? Well, what motivation did we have to do the Canadian surface reanalysis for Kaiser? Well, the focus of the reanalysis, well, the focus of this reanalysis is on the surface. Why just surface? Because it's a less expensive product, which can be produced by focusing more on the following aspect. First of all, the highest horizontal resolution, also coupled runs between surface and atmosphere, and a simulation of observations from surface stations. But we have to know that generally, we don't necessarily have an assimilation of precipitation. When we have access to a precipitation field coming from a reanalysis, it's generally the output of the model, and it's not corrected with observation. In the case of Kaiser, we do precipitation analysis, and here in the graphic I can show you where actually based on spatial resolution and computational time, we can see where are the atmospheric reanalysis. So a weak so some reanalysis have a very high computational cost. Some are called analysis, but they're not really reanalysis because there's no data assimilation like RS5, RS5 LAN, which are products that are forced. So there's no assimilation of data. So we're located roughly in between both. Our computational cost is higher because we do data assimilation, but we can go down to resolutions that are more important because we done data assimilation only in the surface. So the Canadian surface reanalysis is 10 kilometers resolution, and we assimilate, well, we distribute surface variables and also the last levels of atmosphere. But the whole data set that is generated during the production is archived.
So basically, what is the methodology? The third version that will be made public very soon, we're using a very similar methodology. That means that we have a Era 5, for example, a land surface model, and this surface is used to initialize a general model. These are reforecast models that help to have higher resolution regional forecast. And these high resolution regional forecasts are coupled with a assimilation, a surface assimilation model for precipitation, snow thickness, etc. So these coupled models produce a regional reforecast that is then used for surface analysis that is reanalyzed, and this new surface analysis helps us to move over time. The systems used in that section have
décidé de continuer dessus
operational
pour la version
parameters, a
Donc,
paradigm that
chacune
we're
des
using the
composantes,
third
le global,
version,
le
meaning that
régional, l'assimilation de surface, ils ont des pairs
these
qui sont
components
opérationnels à
have
l'Environnement et Changement Climatique Canada au service météorologique.
operational
Il y a une partie de leur analyse qui est
parameters. So part of the
offline, et
reanalysis
vous
is
pouvez
done
le tourner
offline.
après avoir
That
produit
is
la partie
then
en ligne, c'est-à-dire c'est les
used
prédictions
after the part
d'analyse
online,
de
meaning that
précipitation 24 heures. Donc,
these are
ces analyses utilisent
precipitation
le champ
analyses
d'essai qui viennent
24, meaning
des
they're
représentations
using
atmosphériques
the
régionales.
test
On
fields that
assimile
come from
les
regional
observations de surface
forecast.
de précipitation
Then we
sur un
simulate
horaire 3 heures,
precipitations
6 heures, 12 heures et 24 heures pour
over
produire
3,
des
6, 12,
analyses de
24 hours
précipitation 24
and
heures
produce
pour toute la période de la
24-hour
réanalyse
precipitation
à 12
models for
décibels.
the reanalysis model,
Une fois qu'on a ces analyses de précipitation
12Z.
24 heures, on les désagrège basées sur le signal, l'évolution temporelle du modèle
So
pour
once we have
produire
these rainfall
des analyses de
analyses, we can
précipitation
then
horaires.
break it
C'est ce
down
qui,
into
c'est ce à quoi vous avez
hourly
accès
rainfall analyses,
sur,
and this is what you
sur,
have access to.
comme produit de leur analyse. Donc,
This is based on the
plusieurs versions de leur
reanalysis.
analyse. La première version
Reanalysis.
qui a été publiée en
The first
2017,
version that was
c'était vraiment un
published
travail de
in
postdoctorat. Le
2017
global, on avait une vieille
was
version
my
de James qui était la version 48.
postdoctoral
Ça utilise
work.
des RA intérim. Le global, la partie globale était à 50 km, la
The
partie régionale
global
était à 15 km et on couvrait de
was
2010
50
à
kilometers,
2014.
regional 15
C'était pour faire
kilometers,
une preuve de concept.
and
La version 2,
the goal was a
toujours la même
proof of
version 2
concept.
donne toujours la
Version
même
2,
analyse atmosphérique globale. Par contre, le global, là, était à 39 km. Le régional, donc les produits
the
qui sont distribués, étaient à 10 km.
products that
Cette
were
version-là couvrait
distributed
de
were
1000
over
à
10
12 000
kilometers,
km.
covering
On
between
trouvait un petit problème dans la
2010
densité maximale de la
to
neige. Donc, on a
2017.
produit
So we had a
la
bit
version
of issues
2.1,
with the
toujours avec les mêmes
density of
calculations,
snow.
sauf que cette
So we
version-là
produced
couvrait de
another version,
1980 à 2018.
2.1,
Maintenant,
from
la dernière version
1980
de
to
leur analyse est
2018. So
sur
the latest
OpenMSSD,
version
donc
that
la
is
version
about to be
3,
published,
essentiellement 3.1.
version
Elle utilise
3.1
la
essentially,
dernière
is
version
using
de
the
GEM qui a
latest
été mise
GM
en
version,
application en juin
GEM version that was
2024.
put online
L'entrée, elle
in
utilise ERA5 et la
June
partie globale est à
2024
11
using Euro
km. La
5.
partie régionale est toujours à 10 km. Et on couvre maintenant de
The
1980 à
regional part
2020.
is still
Donc,
10
toutes les
kilometers, and then we're now
composantes de la
covering
version 3 de
1980
leur
to
analyse sont
2023.
basées sur
So
des
all the
systèmes
components of version
opérationnels qui
3
ont
are
été
based on
mis
operational systems that were
opérationnellement à la
implemented
mi-2024. Il y a déjà un
in
échantillon de
2024.
données préliminaires qui est disponible
We
sur le
now
site
have
internet que
a
je vais vous
preliminary
partager plus
sample
tard dans la
analysis that
présentation.
I will share a bit
Maintenant,
later on.
plus tard dans la présentation, on va vous soumettre un sondage, on va poser des
Later in
questions.
the
On essaie
presentation,
de
we
définir le
have a
contenu de
poll
la
because we're
version,
trying to
la future
define
version
the
de leur analyse, la version
content
table.
of the
Donc,
future version of
le contenu de
the
la version
version
4 de
4
la réanalyse de surface canadienne
of
dépend des
the Canadian
besoins du
resurface
réseau de Québec. Donc,
surface reanalysis.
je serais reconnaissant de répondre au sondage et aux
We
questions.
would really be delighted if you could
Mais
answer
donc,
that poll.
comment on construit? Je vous ai expliqué la méthodologie. Maintenant,
How is it
comment on fait
built?
pour évaluer la réanalyse
And
canadienne? Comment on
how
les développe?
is
Nicolas,
it assessed?
sorry, I'm going to interrupt you again. Do you mind just slowing down a little bit for our interpreters? They're just trying to catch up to you.
Ok,
Thank you so much.
je vais faire une petite pause alors, parce que je parle trop vite. Ok, donc,
Okay,
comment on évalue la réanalyse canadienne?
so how do we
Donc, pour les
assess
évaluations, étant donné le
this?
coût de calcul
Because
et
of the
l'espace de mémoire que
calculation,
les disques
the price of
que
calculation
les sorties prennent, on
and
évalue
the
généralement sur
storage
un an.
that's
On
necessary,
applique
we
la
do
même
a 1
méthodologie qu'on applique
year,
en
we apply it
production de
over a
leur analyse, à
year with the
savoir
same
on a
methodology
une
during
période
production, meaning
d'initialisation
we
de
have
un
a
mois
1 month
couplé et plus 3 mois couplé,
initialization period
atmosphère
that is
surface. Puis
non-coupled,
après,
and
on
then
produit,
over 3
on
months
produit des
coupled
résultats
for
sur
surface
un an
reanalysis.
complet.
And then we
C'est cette
produce
période-là, cette année-là, qu'on
data
utilise
over a
comme
whole
prédiction.
year. So
On
we're
produit
using that
un
period of time.
échantillon pour une
We
année
produce a
après
sample
2000,
for a
parce qu'on utilise
year
un
after
réseau de données
2000
particulier pour la surface
because we're
qui vient du
using
service
a
météorologique canadien.
specific data
Et
set
on en
from the
produit une autre
Canadian
année
Weather
avant
Service.
2000 parce
And we
qu'on utilise
produce
une base de
another
données
year before
d'observation
2000
externe.
because
Donc,
an external
pour vérifier
database
les
is used for
résultats
that
sur
one.
ces deux
So to test results
parties
over
de la
these 2
réanalyse,
data
on
sets,
produit toujours pour les évaluations ces 2 années. Les évaluations se
we
font
always
sur
have
des
evaluations over
kilomètres de
those
acoustique
2
qui sont illustrés ici en image
scopes of
principale.
years.
Donc, plus tard, je vais vous montrer des
Later,
évaluations pour
I'll show you
chacun
some assessments
des
for
domaines. On a
each
des scores
domains, and
de
we have
félicitations qui
scores for
donnent dans ces
each
domaines-là.
stations under these domains. We use these fields, short-term forecast 6 to 18 hours, and as well a full forecast 0 to 48 hours. Why are assessments 6 to 18? Well, because the way we do reanalysis is to make forecasts every 12 hours and over 48 hours. At that moment, we use 6 to 18 hour deadlines to reconstruct a time series for the 43 years that cover the reanalysis. So we use this forecast to look at the model, but also this part of the reanalysis that is very important because it's distributed externally. The variables that are used for the CASR are the weather forecasts, wind, temperature, geopotential, and the dew point. On the surface level, we're using the Bukovsky areas that I mentioned previously: wind components, temperature, dew point temperature, snow depth, snow water equivalent, and quantities of precipitation over 24 hours and 6 hours. On top of these checks are done, we're also doing verifications over data sets like ERA 5 land, MIRA 2. We're doing time series of minimal temperatures and maximum temperatures verified against observations and also the date of snow melting in the spring. There are a lot of partners, a lot of collaborators, more and more, and we're quite delighted that they contribute to the CASR. Active collaborations are, for example, universities. We've received 10 contribution and grant projects based on the flood hazard map identification and mapping program. We've had active collaboration with the Pacific Climate Impact Consortium, or WINOS, Agriculture and Agri-Food Canada, and as well with Hydro Quebec and the Quebec Department of Agriculture. Data is important because it adds users, but also love to have feedback on how it's used, what were the issues to improve the subsequent reanalysis versions. Reanalysis is also used in historical flooding events. Observations do not cover all of Canada, so we use reanalyses where there are no observations. Reanalyses are also used for extreme events, extreme precipitations, and the conception of hydraulic structures. Reanalysis is also used at the Canadian Weather Service as climate reference here on the right for SWE anomaly based on reanalysis and forecasts of the model.
Les objectifs, donc j'ai un peu abordé ça précédemment
the goals,
dans les différentes versions de leur analyse, mais les objectifs pour la version 3
the goals for version 3
sont les suivants par rapport à la version
are the following compared to the previous 2.1 version. First, to replace ERA interim by ERA 5 for the initialization. Secondly, update the components that I mentioned, the CASR with the latest CCEMEP operational versions from the Canadian Meteorological and Environmental Forecasting Center. So version 3 is all based on systems that were made operational in June 24. Version 3 want to cover 1980 to 2024, but we need to mention that year 24 will be produced and a decade before 1980. Once we've published 1980 to 2023. Also, what was important for us is to take into account the feedback of our partners and collaborators to address the limitations they had identified, meaning the programs with universities and FHIMP. They mentioned that we had a strong cold bias in minimum temperatures and maximum temperatures and mean temperatures during snow melting. Orenos also pointed out, for example, strong trends for temperatures last spring. So we worked to address these issues so that version 3 is not affected anymore by this, and that users could see a positive evolution of that product. Before moving to the next point, I wanted to address the impact. To correct these issues, I'd like to point out here mean minimum temperatures for the month of June. On the left, you have version 2.1 of reanalysis, and in the middle, you have the comparison between 2.1 to ER5, and on the right, a time series of a weather station in BC. What we can see is that there's much less blue for the month of June, minimum temperatures. We see that the cold bias is almost all vanished, except maybe in the Rockies. Need to mention that ER5 is not the exact source of truth, but using it to benchmark. And green is ER5 land, in blue is 2.1, and in pink is 3.1. So you can see that through a whole moment of snow melting in the spring, 3.1 was blocked to 0 until all of the snow melted. Now with 3.1, we see that we can reproduce a time period with variability similar to observations. As mentioned, we test 2 years. Here's mean minimum temperatures for July 2014 for 2.1, 3.1, where blue sort of disappears. And once again, in the time period, we see that the observation is much better reproduced with ERA5 land. That was for minimum temperatures. If we look at maximum temperatures, we see the same strong signal between 2.1, 3.1, and the time period. We see a whole period in the boreal forest where version 2.1 had a very strong bias that up to 6 degrees, while the 3.1 version is corrected. We also see it in the right, where it follows more closely ERA5 land, where the 2.1 version was blocked at between 0 and 5 degrees. That's for 1992. Going to 2014, we don't see as much a strong signal in the boreal forest, probably because the snow distribution was not the same. But we can see in the West, Quebec, and Newfoundland that we don't have the cold bias in the 2.1. And once again, we almost perfectly follow ERA5 land, while 2.1 was blocked between 0 and 5. So this addresses the cold bias in the spring, meaning it was strongly mitigated or even perfectly corrected. This is quite a positive effect of the feedback. Another thing we worked on the third version, well, we changed the grid. It's enlarged to address the needs of different users. We also updated the topography used for reanalysis and operational models, and the 2.1 version. We had an old version. For example, even a ghost mountain in BC. So it improves representativity. We updated all the observation networks that we're using 2.1.
Dans les unités d'épaisseur de neige qui étaient assimilées dans les observations avant 2000. Donc ça, ce bug faisait en sorte que dans la version 2.1, il n'y avait quasiment aucune observation de neige qui était
before 2000,
donc ça a été
meaning that there were almost no snow observations that were simulated. Before and afterwards, we also worked to make some adjustments in the snow because some remote regions there was snow coverage that was accumulated over years that was not sort of reset. We made sure that we had time consistency. Here, I'd like to show you evaluation results. The Canadian Meteorological Service, we love assessment cards. And the left is for temperature, middle is for wind, and right is surface. When it's red, it means it was improved. And horizontal is the different tables throughout the seasons. The figures and the values are the functions of improvement between 2.1 and 3.1 in terms of root mean square of Minsk.
On peut avoir des améliorations, comme par exemple dans le
domaine des the dew point was improved, for example, in the Great Lakes, based on an improvement of 25% over the RMS. We really see positive improvements that go from 25% to a few points of percentage. Wind improvements in all domains are observed. Same for surface pressure as well. Improvements in all domains. The result is that we can see great standard deviations and bias improvements for all surface and atmospheric variables for all domains and seasons compared to 2.1. So this is quite satisfying. Also compare 24-hour precipitation analyses. On the left side of the graph, the top column is frequency bias. In the middle, it's a skill score, and the bottom is based on precipitation. The same chart in blue 2.1 and in red 3.1. In gray, the forecast used as test fields of reanalysis, and in purple also scores for ERA 5 lands were produced. What we can note is that the 3.1 version is similar or neutral or with a slight improvement for 2.1 and the reanalysis for 24-hour precipitation analyses. For the frequency bias, we see that it's degraded for small quantities and a bit of an improvement for larger quantities. Now this is for all of North America. For skill, it was somewhat improved in the winter, and for partial water mass, it's very similar. So that's the main component. What's interesting in this, however, is that we can see that the Canadian surface reanalysis gives much better data in terms of precipitation versus the fields of precipitation used by ERA 5 land. We can see with the frequency for large quantities where there's a deficit of event frequency in large quantities in 50 years. So we see this skill is much better represented versus ERA 5 land in terms of partial water mass. It's similar, but we can see that there is more water in Euro 5 land.
Donc, ça, c'est l'aspect score. On a, en
So
mettant
that's the
à jour
score
les bases de données
aspect.
d'observation
By
au loin,
updating
dans l'image
observational
en haut à droite,
database,
qu'il
we
y
can
a
see at the
à
top
peu
right
près, ça va jusqu'à
that
1000 observations
it goes up
supplémentaires
to
dans ces bases
1,000
similaires qui ont
additional
été ciblées parce qu'on a
observations
mis à jour les différentes bases de données.
because we updated the databases.
Puis ça couvre, c'est pour toute
That
la période
covers
de la RAN.
all
Donc
of
ça,
the
c'est versus la version
reanalysis,
propre.
reanalysis
Maintenant,
period.
si on regarde
Now,
comparé au système
if we compare
opérationnel
it to the operational, the current operational model
par les services météorologiques canadiens.
by the
À droite,
meteorological service,
de carte de
on the
score
right,
que je
we
vous ai
have the
montré
same card scores
dans la
that
version de
I
poème,
showed previously,
mais
the
contre le
scorecards,
système régional de prévision
but
déterministe. Donc,
versus the deterministic
CRPD ou
regional
RDPS en
system,
anglais. Donc, on voit que par rapport à
so
ce système-là, on a la
RDPS,
même configuration atmosphérique.
and we see that we have the same
C'est uniquement les
atmosphere
analyses qui sont utilisées pour
configuration
partir des
used
simulations. On voit qu'on a des
to start
améliorations
simulations.
significatives,
And we can
à part
see
dans un petit
significant
domaine de
improvements,
Bukowski qui
except
est sur les
for
États-Unis, au
a small
sud-est,
Bukowski
sud-ouest des
model in the
Donc, de
southwest
manière
of the
générale, on voit des
US.
claires
But
améliorations pendant l'automne.
we
On
see
a un
clear
hiver, en fait, toutes les
improvements
saisons,
in
peut-être
all
une petite
seasons,
dégradation en termes de
maybe some
température absolue
degradations in terms of absolute
et un peu de
temperatures
rosée sur
and dew
l'Arctique
point
en
in
été.
the Arctic in the
Au
summer,
printemps, pardon.
or in the spring rather.
Comparé au système de prévision haute
Compared
résolution
to the
précédent,
high resolution
opéré
deterministic
opérationnellement par le
provision
gouvernement du Canada,
system
donc
previously
HRDPS,
operated by
SHRPD,
by
le résultat est plus nuancé. Ce
metro,
modèle-là, il n'est pas la même
the Canadian
résolution,
service.
2,5 km
The results are more
Par
nuanced.
contre, ils utilisent une
They were
méthodologie
using
similaire
2.5
pour la
kilometers, we're at
simulation.
10.
Donc, on voit que par exemple, dans le domaine Est ou sur le Grand
For
Lac, on a
example, in
des
the east
dégradations. Dans
domain,
les
we
régions
have
alpes, on a des
degradation. In the
améliorations.
Arctics, we have
De façon
improvements.
générale, on voit des
The
améliorations importantes par
overall,
rapport au
we see
modèle régional
improvements versus
et
the
des
regional
résultats qui
models
sont
and
plus mitigés
results
par
that
rapport
are
au modèle
more
haute
mitigated
résolution
with
canadien.
regards to the high
En termes
resolution model.
d'épaisseur de neige,
Now, with regard to the
d'équivalent anneau de la neige,
snow
à gauche, les images
thickness, the
illustrées à
snow
gauche,
depth
et en termes de
on
précipitations
the
à droite. Donc,
left
la
and
neige
precipitations on the
n'a
right.
d'épaisseur que l'équivalent de la neige. On se situe, on a des scores qui sont
Our
relativement
scores
similaires,
are quite
soit
similar,
au modèle régional, soit au modèle à
either
haute
with the
résolution.
regional or high
Tant
resolution
pour
models,
le
and
biais
both
que la
for
RMSE.
bias and
Dans ces graphes, les couleurs sont les stations
RMES,
manuelles et
RMSE.
les bandes assurées sont les stations automatiques.
And
Donc,
the
c'est
checkered are automatic
des scores qui sont
stations.
faits pour les différentes régions de Bukowski.
Strips,
Donc, on voit qu'on se situe
sort of
entre les deux
bars
modèles.
are automatic stations.
Par contre,
The rest
de
are
façon
manual.
générale,
And we
on
see
est
that
un peu
generally
moins bon que ERA 5
we
pour la neige.
are not as good as
Typiquement,
ERA 5
on a
land for
étudié différents.
snow.
En termes de précipitation
For
versus
precipitations versus
l'analyse de précipitation opérationnelle
operational
opérée par
precipitation
le
analysis operated by
le Centre de prévision météorologique canadien,
the
on
Canadian
voit qu'on est très
service,
similaire
we see
aux
that we are
résultats,
quite
tant en
similar
termes
to the
de
results
fréquence
for
que de
both in
VS,
frequency
de masse
bias
partielle d'eau. Donc ça, c'est
as
intéressant
partial
parce
water
qu'en fait,
mass.
on peut
That's
utiliser
quite interesting because
les analyses
we can
opérationnelles
use
pour
operational
prolonger l'archive de leur analyse parce que les résultats sont très similaires.
analysis to
Donc,
extend the
comme je le
archive
disais,
of the
épaisseur
analysis.
de
So as
neige,
mentioned
la bande de
previously,
neige, on
snow
est
depth
entre le modèle régional
and
et le modèle
snow
à haute
water
résolution.
equivalent. We are in between
Au
the
niveau
RDPS and
opérationnel, pour la
RDPS, so
précipitation, on est très similaire
a
à
bit worse than
l'analyse
ER5 land, but for
régionale de
precipitation
précipitation
analysis,
déterministe.
we
Quand on
are
utilise la
very much in
version
agreement with the
infraradar,
RDPA when
en
using
termes
the no
de
radar, no
fréquence et
satellites
de
version in
vitesse.
terms of frequency bias and ETS and
Une preuve
partial
de
mass.
concept, donc
The proof
on
of
a pris une
concept,
version préliminaire du
we
système
used a preliminary
de
version
la analyse canadienne version
of
3
the
pour faire des tests sur
version
les années
3
1972
to
et
run
73.
tests
Donc ici, on
on
voit par
year
exemple
72-73.
l'impact pour ces
Here we see
années-là.
the impact
Encore une
over
fois, en
these
rouge,
years. Once
c'est
again, in
la version temporelle
red
de leur analyse. En
is
violet, c'est ERA 50 et
3.1,
en gris,
and purple is ERA
et
5 land, and gray
c'est le champ d'essai de l'analyse de
is
précipitation.
the
En haut,
test
c'est les tests
fields
de
of
classe. En bas,
precipitation.
c'est les équitables site
Bottom
scores. Donc, on
are
voit pour ces années-là, 72-73,
equitable
on
site
a des
scores.
résultats qui sont corrects et qui
Scores
sont
are
mieux, encore une fois, que
correct
ERA 5
and
pour la précipitation.
better
En
for ERA
termes
5 land
de
for
neige, donc,
precipitation again.
on
Now, as
a
for
modèle
snow,
neige et épaisseur de
equivalent,
neige. On voit aussi qu'on a
water
des scores qui
equivalent,
sont
and that
similaires
our
à
scores
ce
are
que sont
similar
obtenus par ERA 50
to
pour les années
what ERA 5 land
1972-1900. Donc, c'est encourageant.
has
Ça
for
nous a permis
72-73,
décider
which is
qu'on était
encouraging.
capable d'aller plus tôt
It
que
motivated
prévu
us to
en utilisant ERA 5 comme pilote.
to know that we can go before 1980 in the pilot. There are two subproducts in the, as they say, the Casser Land and Casser River. Why two products? Because of the methodology of reanalysis, because of the soil water content, snow depth, snow water equivalent. The gain of the Casser is sort of, it's not optimized to have the best possible results for soil. So we have these two products, and with these two, we improve forecast for snow in terms of bias and RMSC, both for dew point, surface and soil. Casser River covers most Canadian watersheds, in flow and river flows. So we simulate river flows in Casser River, and it covers the same period as the Canadian surface reanalysis. But now we have these 2.1 products. They will be publicly distributed. The next step is to do it based on the 3.1 version. On the right, or on the left rather, we have the domains of the different watersheds distributed for Casser River, and on the right, what is covered by Casser Land, the black box.
So here is just an illustration with the scorecards of the results for the Kaiser Land versus Kaiser, with also preliminary test for the version 3.1. So we can see essentially for the various domains and for the various periods of time during the year, the improvement that we can have on top of the Canadian surface reanalysis of version 3, the improvement that we get from Kaiser/Land version 3. So these improvements are 1 or 2%. So it's very interesting. On top of that, with this system, we have access to better variables for water content of the soil, the runoff, and so on. So it's a product which is very interesting for hydrological purposes. To the right, I'm showing preliminary scores for the snow water equivalent. So we still have to work on it, and we have the hope of improving this. Now, if we use Kaiser Land and Kaiser Land and Kaiser River, it allows us to test more advanced models, which would be too costly to test directly. So this allows us to do preliminary tests for the future versions and implement these models in the next versions of the Canadian surface reanalysis. For example, in version 4, we're going to use a more advanced surface schema, which is currently used in Kaiser Land. Now, concerning the disseminated variables for Kaiser, the guidelines for data dissemination is we only disseminate evaluated surface variables, and which allows us to drive hydrologic and land surface models, for example, precipitation, dew point, wind direction and speed, pressure, and downward solar flux and infrared flux, and so on. So in version 3.1, we use 24 hours precipitation analysis, and we distribute the types of precipitation. We distribute the analyses of the temperatures and dew point. And we also distribute snow depth and the snow water equivalent. We have to know that these two last fields, the quality is lower, and if we want the best quality possible, we have to use our cast land, the Kaiser Land. So for the previous versions, the Voyager 2.1 and before, it's distributed on Canadian Surface Prediction Archive, or CASPAR. So it covers in North America for the years 1980 to 2018, and we can do queries for certain variables. It's also used by Uranus Pavix, so it's only specific variables on which we can do statistics to obtain results. Now, version 3.1 of the reanalysis will be available on Caspar, like version 2.1. It'll be also available on Uranus Pavix. But now we're disseminating the data on a collaborative cluster of ECCC, i.e. GPS-SC. We have the hyperlink. There is more documentation available there, and we're currently there's a sample of preliminary data for the past 10 years, but we will distribute soon the whole reanalysis. The long-term objective is to disseminate the Kaiser in the usual channels, the Canadian Weather Service channels, Data Mart, and Geomit Climate. Now, to conclude, and the upcoming steps, well, Kaiser 3.1 will soon be released. It's just a question of days now. We note important improvements compared to Kaiser version 2.1. We've done a lot of work to refine surface-atmosphere interaction in order to mitigate the spring cold bias and spurious temperature trend issues. We will soon, once it'll be published, we will do a back extension for before 1980. There are two additional products associated with the Kaiser land, Kaiser land and Kaiser River for better results, and to have the flows of rivers and the river analysis, and it's distributed on a new platform and documented on the website of the GPS-C. So there, you have probably received questions, and we're currently defining the contents of version 4 of the Canadian Surface Reanalysis, and we'd like to know what would be more useful for you. Perhaps shorter periods, which would cover from 1990 and 2000 to the current time, with a configuration and a resolution which is more advanced, i.e. 2.5 kilometers, 5 kilometers, and an assimilation of data, satellite data, or do you prefer a version which covers a longer period, i.e. from 1950, at the same resolution, and with an assimilation that would use punctual or spot surface data? So this might improve the precipitation analysis. So in other words, it's a question, the other question that we're asking ourselves is, do you still need that we cover the whole North America, with a similar resolution to version 3, or could we do a smaller domain with a higher resolution, for example, cover the same region as the river Canadian Surface Reanalysis, which only covers the main watersheds of Canada? So I'm curious to see the results of the survey. Thank you very much for your attention, and I'll be more than happy to answer your questions. So, do you need Kaiser to be updated on a monthly basis to reach current time? Quasi-operational. Number 2, what domain size do you need for your application? And question 3, what resolution is sufficient for your applications?
Thank you, Dr. Gustav, for your amazing presentation. I'm just going to pause for a moment here for folks to participate in the poll. If you missed that, there should be a poll that has popped up on your screen. You could just take a minute or so to complete your answers. This feedback will be really helpful for Nicola and his team. Okay, so I'm seeing lots of answers come in. We'll just leave that on the screen. Thank you again, Dr. Githa, for your presentation. I'll actually jump right into the panel discussion, seeing the time. So I'll invite Emmanuel as well as our other speaker to turn on your camera for the panel discussion. And this is just a couple questions that we've prepared in advance for the speakers so that we can learn a bit more about their work and hear some more of their insights. So I'm going to pass it to Emmanuel to ask the first question.
Our first question is, what do you see as the next big breakthrough in your field? How might advances in machine learning, remote sensing, or computational power change the way that we predict and mitigate environmental risks?
Oh, let Nicola go first.
Okay. There are several aspects with machine learning that could help us, and remote sensing too. As I said, the next version of the reanalysis, the Canadian surface reanalysis, we are willing to use satellites, so remote sensing. The problem with that is, for example, satellite data that discovering long periods does not exist for surface. For example, iMerge for the precipitation is covering just starting in the 2000. For soil moisture, surface soil moisture is similar, it's starting around 2000. And for snow, IMS is also starting in 2000. So one of the application of artificial intelligence will be to extend in the past, based on the result from shorter period of the reanalysis, the data sets. So this is one of the application, but there are a huge amount of applications such as doing some quality control of observation that are used as input of the reanalysis. Also, the same thing have the way we perturb the field in the ENKF, which is used within the reanalysis, instead of having something which is deterministic and add some random noise, we could use artificial intelligence to produce some realistic noise based on temporal evolution of the noise at some grid points and things like that. So I think there are a huge amount of application of artificial intelligence and satellite data.
Tadros, do you want to chime in on that one?
I can probably add a little bit as of course the dream would be to have an ice jam early warning system that is how do you say this? That is alive, that is adjustable, that we can fit from a spot to another easily with predetermined parameters or setup. Of course, to have a reliable, transferable system that is able to learn from the historical data is a dream. I think that would be a breakthrough in my domain and would benefit from the work that Nicola's doing. We already integrated the prediction in our fuse system, so hopefully with the knowledge we're developing. And then I've seen quite a few questions in the chat here that are actually mostly the same question as how can we adapt what you're doing here to other rivers and stuff, and this is the dream. Like if we have the wealth or the opportunity to collect very detailed data and analysis and procedure, this is basically give us the chance to go coarser and coarser in the data requirements and in the results, and see how with less data, with less information, we can still get acceptable results. So that would be the opportunity we have in this research. But that would be my intake on this.
Thank you both. I'll just ask one more panel question, and I'm seeing lots of questions in the Q&A tab, so please feel free to keep them coming, and it's helpful. I've seen a couple people do so. If you want to address a speaker, please let us know who you want the question to be addressed to. So my question for speakers is, when modeling river ice processes and land surface processes, one must pay close attention to the surface energy balance. What are the main challenges that you face when trying to improve the surface energy balance in your model?
Me or Nicola?
Go on.
Okay. Okay, so I can go ahead quickly. So I think of course it all depends on the type of river ice surface. So we have rubble ice in a jam, different than a little bit of open lead, different than pure thermal ice that is exposed to the environment, different than an ice cover in a very snowy area with a huge cover of snow that is insulating or wet or whatever. So this question is very interesting because if we have continuous, what I mean by continuous, but in a reasonable temporal time step, like a daily or whatever, or even 2 days of the surface ice condition in the river that is processed and readily available, this would be a huge improvement to our prediction of the heat exchange with the ice cover. And this is a main input to any predictive model we're using for the ice jams or even under ice discharge. So that would be the big wish that we would have, is a continuous condition of ice over their study reach.
Concerning the reanalysis, the surface energy balance, and the conservation of water. For now, based on the system we are using, it is not meant to be properly reproduced. So that's why it is tweaked, and it has been tweaked because it's the way, like the paradigm we are following is using the operational system, and those systems have been tweaked for years to produce the best results for the surface and the lower part of the atmosphere. So for the version 3, that's why we are just distributing the fields from the lowest part of the troposphere. And that's why we are also doing another, like the associated product, which are Kaiser Land. Kaiser Land have a much better, much advanced surface model, which is much more representative in terms of energy balance, and it is conserving water. So that's why we have those two products. In the future, we are planning to use the same surface model that is used in Kaiser Land in order to improve the surface energy balance and to close the water bilan. So that's what I would answer.
Thank you both. So now we'll jump into the Q&A tab, and what I'll do is I'll take a mix of chronological order and then also alternating between the speakers, just so we have a nice balance. At this time, we have about a little bit over 10 minutes left. If you'd like to ask your question live, please raise your hand and we can actually allow you to unmute and ask the questions live to the speakers. So first one I have here from David for Tadros. Thank you for an interesting presentation. Can you comment on the potential to generalize the knowledge you're building on threshold behavior so that it can be applied to guide analysis on other river systems? For example, where the time and financial resources aren't available to support a similar research initiative.
Yeah, that's a question we do actually have as well as a research team, but I appreciate being able to discuss a little bit here. So the idea is to see if like what would be the most important parameters to actually track or measure over a river, over an interesting reach. Now, if we have all this wealth of information, we can gauge which ones governs where. And then hopefully with this kind of information, we can go coarser in resolution, either in the amount of data or along the river reach, and see how these affect the accuracy of the forecast. When you start on a specific reach or a zone when you're monitoring, so understanding the processing, having a little bit of history of how ice forms and deteriorates and breaks, those are undeniable. Those has to be there in terms of knowledge. But then going forward with this, maybe the work that we're doing and my team at ULaval would help direct which kind of investment we need to put towards developing an early warning system. Is it a full coupled model or a threshold model or a simple relation between just two parameters? Hopefully with the integrated approach we're taking, we can have more guidance on this. I didn't present this, but there is a guide we're working on for Ministry of Public Safety that details the development of an early warning system for ice jam flooding, and this has a very detailed flow chart for the amount of data versus investment that needs to be taken into account based on the level of sophistication or the river or the risk to be taken. So this will come hopefully in a year or so, and it will answer some of those questions.
Thank you, Tadros. And I think that might apply to the next question from Paul, who's typed in here as well. So hopefully that addresses their question. A question for Nicolas from an anonymous attendee. Can you explain a bit more what the difference is between RCAS and ERA5L? I understand that ERA5L has a finer resolution temporally and the same horizontally. When might you use one versus the other?
Okay. So in ERA5 land, there's no assimilation or observation. ERA5 land is a surface model which is forced by ERA5. ERA5 land is 9 kilometer resolution, and we have access to the data at the hour, every hour. So we are at 10 and we produce the data every hour, and ERA5 is 9 and is producing the data every hour. But ERA5 land is global and is updated operationally. So the main difference is that on Kaiser side, we are assimilating surface observation of absolute temperature, dew point, snow depth, and precipitation for the various accumulation periods. Why there's no assimilation in ERA5 land. So this is the main difference. ERA5 land is just a surface model that is run offline while we are simulating observation. So that's the main difference. From the second part of the question, which is which of the variable I would trust more in ERA5 land and in Kaiser, I would say this is a tricky one.
Yeah, when might you use one?
Yeah, well, for precipitation, there's no question. Precipitation is much more precise in Kaiser. This is clear from the scores, from what we see. Precipitation, we assimilate observation, and we see clearly that is the analysis of precipitation are much better in Kaiser. For surface temperature and dew point, I tend to think, and the scores and the differences we produced are showing that results are fairly similar. But the fact is, if you use precipitation from Kaiser, you better use temperature and moisture from Kaiser too, because it's more consistent than using variables that are coming from different data sets. Then for the snow, and also the answer to this question, it depends. It depends where, it depends when. For example, the snow in the southern part of Canada, where there are observation, I think it is, well, the scores show that we are not that as good as ERA5 land. because the model we are using for the snow, even if we are simulating observation, is not as advanced. But the snow in the coastal range of the BC and the western part of the country, ERA 5 land has a huge amount of snow. It is written in their paper that it is not, it is incorrect. So it is none. And so maybe in that part, the snow we produce is better. Yet all those answers are based on what we have done so far. We were evaluating on just 2 years. So now we are evaluating the whole data set, and we produce more statistics for the whole data set. So soon we have, and in the paper we are preparing, we try to answer those questions, which are really interesting.
Thank you. Next question, I believe it's for Tadros from Sujata. Has this coupled modeling approach been tested on rivers with different hydrological and ice conditions? Just wondering how scalable this framework for different river systems with varying ice and hydrological conditions.
Okay, so this is actually the funding for the current programs that are having from ECCC is so based on the work we've done or we're doing on the Chaudière, we propose to do a comparative analysis. So the project would answer exactly this question. So we're taking 3 watersheds. So the Chaudière is one, and then one in Ontario, one in Alberta, with different environment, different sizes. So 3 watersheds with different sizes, different environment. And then on those 3, we're doing 3 approaches. One would be the coupled model of a process-based hydrologic model with a hydraulic model. And then the second level of approximation is lumped hydrologic, which is like Hoopla, which is probabilistic and a little bit for the hydrology with hydraulics. And then the third level would be a backwater empirical model based on our knowledge. Then apply this on the 3 different watershed with 3 sizes. And hopefully within this project, we'll have the conclusion to say, okay, the amount of gain in the accuracy going from a process-based model to a lumped model to an empirical model is what, based on which size and which context of river. So the answer to this question is in our mind, and this is the focus of the current funding was the program with ECCC.
And then I think as a follow-up to that question, can you also comment on the role of climate change in altering ice jam flood risks and how these model and frameworks could account for these changes?
So when we think of climate change, and this has been the buzz for the past 10-15 years, is there is warming, there is more peaks, less intense, less prolonged winters, and things like that. So this is undeniable. Like we're seeing this, but when you take this general statement and apply it to ice cover condition, the complication comes in the physics, because the scenarios that we've been observing in the Chaudière the past 5 years is repeated. So we have an ice cover that forms in early December, late November, and then we have a midwinter breakup. This is new now. This is climate change that comes in end of December, in January sometimes, with maybe sometimes atmospheric rivers or big rain events. The problem is now not all the river are reset. There are some rivers or some sections where, due to the midwinter breakup, there forms some tiny little jams because the ice that have been formed from December until early January is not as much. So those are tiny jams that nobody cares about in terms of flooding stress. But now the risk comes in the spring breakup, when you have this little jams that nobody noticed, that builds ice during the rest of the winter until you come in late March or April, and this becomes a huge obstruction and a location that has not been known for jam before, or has not been anticipated during to our threshold methods, or our historical data doesn't tells us, for example, that those conditions would cause jamming or flooding. but if we didn't take into account the effect of climate change to actually form those little, we call it in French bouchons, but I don't know the translation in English is what. Maybe Nicolas can help me. Like when you put into a the bouchon,
like
so like when like the things that you have in a champagne bag or whatever. So those little things nobody cares about during the midwinter, right? And it doesn't cause flooding, it's nothing. But build on a meter ice jam and then thicken it a little bit more, and then having even little flow coming by, it will not pass, and then it will cause flooding, although the conditions historically wouldn't tell you there is flooding. So the effect of climate change, I've been seeing it the past 4 or 5 years in this context. Like the other contexts are known and are easy to explain, which is more intense, warmer, less in duration, more stronger peaks. But in terms of physical process on the rivers, the story that I just told you right now is super interesting. I've been documenting this as much as possible because even for mitigation measures, now we recommend that municipalities don't wait until March to start weakening the ice. But if there is a midwinter breakup, just go observe the river. If there is a tiny little spot where ice is still there, just break this one, let it go, because otherwise it will build on it in the spring. So anyways, lots of stories this way.
Thank you. Thank you so much. So I see we've run out of time, so my apologies, we couldn't take all the questions today, but thank you so much to our attendees for being so engaged in our presentations, and thank you to our speakers for spending their afternoon with us today. The recording of today's webinar will be available on the CWRA website. We hope you will join us for other webinars in this series. The last one is happening next week. We'll post some links in the chat for some relevant topics that we've covered today, and also a short survey will just pop up on your screen regarding today's webinar. Your feedback is really valuable and will help us improve future sessions. So thank you again for all your time. We're going to turn off our videos now and leave it running so that you can take a couple seconds to complete the poll and grab any links that you might want from the chat. So on behalf of CWRA and our excellent presenter team and our interpretation team today, we thank you for your time. Have a great rest of your afternoon. Take care.